talk about cloud native and basically how to design cloud native applications. My name is Bilgin Ibryam, and I work for Red Hat as a consultant, so I help customers use our products. These are mainly integration products such as Apache Camel, Graph, ActiveMQ. No idea how it's going to work. After using Camel and the other integration products for a couple of years, I have written down Camel Design Patterns book, which basically explains the different use cases and my learnings from that experience. And recently, in the last year or two, at Red Hat, we start using Kubernetes through OpenShift. So we start running Camel, ActiveMQ, and other related integration products on top of Kubernetes. And me and my colleague Roland, the previous presenter, we start documenting these different patterns, use cases, and learnings. This talk will cover some of those learnings. Let's see how this goes. The agenda today look like this. We'll look at the different cloud native ecosystems. I don't have to move. We'll look at the different cloud native ecosystems, what primitives and abstractions these cloud native platforms provide, then what design principles emerge from those primitives, what patterns are there, and what are the benefits of cloud native. So let's get started. I'm sure you all have been to enough microservices conferences. This is the only slide that mentions microservices. And there are lots of definitions about microservices, but the one that I think is relevant to this talk is that microservices is an architectural style that trades code complexity for operational complexity. That means microservices simplifies the code itself. You have lots of smaller microservices, but the operational complexity increases a lot. And to be successful in microservices, I'm sure you all know you have to have good configuration management, tracing, distributed tracing, centralized metrics, centralized logging, etc., etc. Actually, if we look further, to be really successful in microservices, there are a lot more areas that you have to cover, that starting from infrastructure automation to CI/CD, all the application level automation, and even at the team level, moving into more DevOps and to DevOps style of working. And cloud native has been born and emerged as a response to these needs of microservices. Here we can see where, for example, Kubernetes fits in this pyramid of needs for microservices. As you can see, it covers quite a lot of it, and basically cloud native is an answer to the microservices demands. Now, trying to define what is cloud native. There are lots of definitions, but the one I like is from Joe Beda, one of the Kubernetes founders, and he says cloud native is a way of structuring teams, culture, technology to utilize automation architecture to manage complexity. As you can see, cloud native is not just, let's say, Spring Boot or just Kubernetes on its own. It touches on team, it touches on culture, technology, and architecture, and all that. And if we look at some of the common characteristics of cloud native today, these bits are constantly evolving and changing. Cloud native applications typically are creating using microservices architecture. They are packaged in container, which are managed by platforms on top of cloud infrastructure, and usually done through practices such as continuous delivery and DevOps. So if you are doing, I would say, most of these, you can say you are cloud native. Or if you're wondering what's cloud native, I would say it's a collection of these characteristics. Maybe you are not using containers, maybe you're using Amazon Lambdas or something else, or maybe you are not using microservices, but or some other architecture. But if you have automation at the infrastructure, at application level, and some kind of continuous integration and DevOps culture, you can say you are cloud native, I would say. If you look at the brief history of cloud native or cloud as a whole, here are some of the important milestones that brought us today. The few key ones are the virtualization introduced in early 2000 by VMware, and then Amazon offering it as a service. And then in 2009, Heroku introducing the Heroku platform with its definition of 12-factor apps. Probably that was the first generation of cloud-native application. And then Cloud Foundry basically creating an open source version of Heroku. And up to that moment, this was, I would say, the understanding of cloud native. But then Docker coming in 2013 and redefining how we package and ship applications, and Kubernetes in 2015 kind of redefined what is cloud native. And today, if we look at the cloud native landscape, it's you can see it's quite huge. Basically, there are so many different ways to be cloud native, starting from infrastructure automation, provisioning, runtimes, orchestration. You can pick and choose all kind of tools and still basically be cloud native. I would say from developer point of view, probably the landscape is slightly simpler, because we have at the moment a couple of different ecosystems of cloud native platforms. So probably as a developer, as a company, you kind of belong to one of those rather than multiple of these ecosystems. You're either using Cloud Foundry, using all the Spring Stack, or maybe you are using Amazon ECS, the container services with all the other surrounding Amazon services, or maybe just pure Docker, or maybe you are in the Apache world or Apache Mesos, and the Kubernetes ecosystem with Kubernetes and the surrounding forks. But probably as a developer, you will start in one of these ecosystems, and it will take, I would say, months or years to really be productive and good in one of these ecosystems. And switching back and forth is not easy. And here I try to put together some of the concerns you should keep in mind when you are maybe choosing an ecosystem. Just to give you a few examples. For example, the governance model. If you pick Apache Mesos, you know the Apache projects that are governed by the PMC members, so there is certain release cycle, there is certain voting, so releases cannot go that fast. Maybe, or if you pick Amazon ECS, you have to wait until the next Amazon Summit to find out what new features are added and what's coming. If you pick Kubernetes, Kubernetes is part of the CNCF, Cloud Native Computing Foundation, and as such it is driven by the Technical Oversight Committee, so members of the Platinum sponsor. So all that defines how the project will be governed. Then you should check which are the supporting organizations, so what companies are backing that platform. In case of Amazon, there is just Amazon. In case of Kubernetes, there are lots of big companies such as Google and IBM, Red Hat, etc., etc. In case of Mesos, that would be mainly Mesosphere and HPE. So it's important to find out which organizations are backing the platform, as some platforms like Fleet were deprecated recently, so the platform can just disappear instantly. It's also important to check the user community. If all the users are enterprise companies, that probably, and you're a small startup, maybe you will find difficult to provision 30 VMs to run Cloud Foundry. So all that kind of makes a difference. And the next aspect is culture and way forward. What I mean by that is, for example, if there is a bug or you want to see how a feature works, you can just go into Apache Mesos and check out the code and see what's inside. Same with Kubernetes. You can go to CNCF and find out who is working on a feature and how you can do pull requests. You can check what's coming in the future versions. But if it is Amazon ECS, you don't have that visibility. It requires different way of working with the platform. Is that off? No. I think only then the technology comes into place. So technology, I think, is important two aspects: maturity and potential. In case of Kubernetes, which we are covering in this talk, Kubernetes has been created based on all the principles and learnings at Google based on the Borg system. So it has a maturity in terms of principles and ideas. And in terms of implementation, it's quite new. It's only 2 years old, but I would say because it has been created after Docker was invented, so it's container first platform, it has a big potential. So I would say in technology, it's quite superior. And in cloud native, it's not only about just a platform. There are always lots of supporting tools, which we'll see in a moment, that you have to use together with your platform. So you have to check what supporting tools are there, and also important to things like documentation, conferences, and books. And I would say the coolness factor, is it how developers feel working with that tool. If it's an old tool, maybe you will find it difficult to find motivated developers. So all that kind of plays a role when you're choosing a cloud native platform. I just want to give you an example about the Kubernetes ecosystem. So these are members of the Cloud Native Computing Foundation, where Kubernetes belongs at the moment. You can see which are the companies kind of backing this foundation. There are lots of those. You can see what other projects are part of Cloud Native Computing Foundation. So it's not just Kubernetes. Kubernetes was the first one, but at the moment there are 10 other projects which complement Kubernetes. So they provide additional tools, things for monitoring, tracing, networking, and service mesh, etc., etc. So there are lots of other projects. And this is kind of the potential future projects that may join CNCF. This is similar to Apache Pollink, where the foundation is looking at some other projects which have similarities and soon may become part of CNCF. This is just an example how the ecosystem of products around Kubernetes is growing slowly. That was the ecosystem, just to give you an idea what's cloud native. Now we'll look into the more developer-focused areas like primitives and abstractions. If you are going to create let's call it a microservice in Kubernetes, you can see here in the red line where your code belongs. So it will be in a Docker container, but as you can see from this picture, there's actually quite a lot of other objects that you have, or abstractions and primitives you have to create as a developer to manage your code. And this is just abstractions and primitives that the developer would use. There's a whole set of other primitives that probably an administrator will use to manage the Kubernetes cluster. But your code will belong to a pod, which can be created by 5 other means, such as daemon set, replica set, stateful set, etc., etc. So there is quite a lot of learning curve to learn such an ecosystem. If we look at any of these cloud native platforms, I would say they more or less provide same set of capabilities. So they are now all support containers in the form of Docker. Previously, Cloud Foundry was just Garden, and Mesos had its own format, etc., etc. But now they all have added Docker. Then they all do some kind of job scheduling. They have container orchestration and application orchestration. But more importantly, I think from my point of view, they provide a common abstractions. For example, they all use container, where you package and deploy your business logic, but they always have the concept of deployment unit. So you never deploy just a single container. You deploy in Kubernetes that spot, in Amazon ECS, that's a task group. In Mesos, there is again a concept similar to pod. So they all have this deployment unit abstraction, which can be a single container or multiple containers. They all have ability to do regular jobs, so they provide ability to service discovery. In Kubernetes, that would be the service. In Amazon ECS, that is the application load balancer. So they have ability to do service discovery. And the reason I'm saying this is that these new abstractions and primitives kind of give rise to new patterns that we've seen in the previous talk. In the object-oriented world, we have things like classes, objects, polymorphism, encapsulation, and the design patterns, object-oriented design pattern book is built on top of that. But when we deal with, in the Java, there is a specialized patterns for Java, which is an example of object-oriented language. But as a developer, when you think about how would you do recurring jobs, you think about executor service, or how you would do initialization, you think about the constructor. But in the cloud native world, when you think about this kind of task, you have in mind, I would say, new primitives. Let's say you want to do service discovery. You don't think only about how I do service discovery in the JVM. Now you can use service discovery at Kubernetes. Or maybe you have a recurring task. In the Java world, you would think about some kind of timer or thread that's recurrently occurring. In this new distributed world, you can use a cron job managed by Kubernetes. So you would say the new distributed mindset, you have these local primitives and abstractions and the distributed one, and you can use a combination of those to create your application. Here I just created a table with the similar concepts and similar concepts or concerns and how they are implemented locally in a single JVM and how they are done in a distributed way in Kubernetes. You can swap some of those, or some of those are supposed to be complementary. For example, the way to encapsulate some logic in the JVM is through Java. In Kubernetes, that's containers. The way to do initialization would be a constructor. So a constructor in Java is guaranteed to run as a first thing when an object is created. It's guaranteed to run only once. It's guaranteed to run in a sequence. Similarly, there are init containers in Kubernetes which run before your application container. So they are guaranteed to run in a sequence, and they are guaranteed to run until completion. So you could think where you can put your initialization logic, whether that would be in a Java or you could use a container to do that. For cleanup logic, in Java, you could use a finalize or some kind of shutdown hook. In Kubernetes, there is a proposal at the moment to create something called defer containers. So that would be a container that's running when your pod is shutting down. So you can do some cleanup the file system or clean up a database or log something. The point being, now you have these two sets of primitives that you can choose when you are creating your applications. You don't have to do everything in the JVM. You can do some of these tasks in the platform. You can see other tasks if you want to run something in the background. Previously, we just had the option basically for a thread, which runs in a JVM, or a cron job, which is on a single machine. But you can use a Kubernetes cron job, which will be a task that is distributed across multiple nodes, and it still runs periodically. And a few other examples for configuration management, etc., etc. So we have new primitives. I would say the next kind of step is the principles similar to solid principles in object-oriented world. I'm sure most of you are familiar with that. Principles are the generic guidelines that you would follow when you are creating your applications. So here I created 7 principles. I just call them solid, but they don't make up the solid acronym, but 7 principles that you can follow when you are creating containerized applications. And if you follow these principles, you are likely to end up with containers that are going to be good cloud native citizens on any of the platforms. So let's go through some of these principles. The first one I called is single concern principle. It is similar to single responsibility principle in the object-oriented world, but the idea is don't try to put everything, all kind of concerns in a single container. You have to think that there is also this abstraction of deployment unit pod. So if you have 2 concerns, you can put those into 2 separate containers and have these 2 containers collaborate between each other. This way you can basically have better reusability of the individual containers for different purposes. And here are concrete examples of patterns like a sidecar, ambassador, adapter, or init containers or defer containers. So if you have to do some initialization, you don't have to script all that in one container where your application is. Maybe you can split the initialization logic in a separate container and have these 2 containers deployed as a single pod. Second principle is self-containment principle. So when you are creating a containerized application that is at build time, you add everything that application needs to the container. And the only exception would be things like configurations and some file systems that you have to mount at runtime. But your application should contain everything. For Java, that would be having Java installed, having your maybe some kind of Spring Boot or app server there, and also your code deployed. An anti-pattern here I've seen is in some places described as the locomotive pattern, but the idea is if you have a container just has, let's say, the app server, and you have other containers which contain your war file or ER file, and you run them together. So your ER file depends on the app server container in order to run. In this case, it's your application is not self-contained. It depends on other containers just to run, which is an anti-pattern. Another pattern is immutability principle. So when you are creating a containerized application, you have to make it sure that that application will run on all environments just by changing configurations, rather than creating separate container for separate environments, or maybe changing the container a little bit for each environment. This is also called as dev prod parity in the 12-factor apps principle. Another, I think, a very fundamental principle is the high observability, and this is kind of a new requirement. Previously, before Cloud Native, we didn't have to add health check endpoints to our applications, but now that's a mandatory thing. So your application has to provide a way for the platform, in this case Kubernetes, to perform things like readiness and liveness checks. By default, Kubernetes will perform process health checks, so if the process dies, it will restart it, but that's not always enough. We know many many cases where a JVM, the process can be still up but non-functioning after running out of memory. So such a problem, process health check would not catch. But if you have readiness and liveness endpoints, Kubernetes can check the health of your application and, if necessary, restart, etc., etc. So I would say this is one of the fundamental prerequisites to be a cloud-native citizen, just to add these endpoints. And there are already in the Java world good libraries who provide that capability with Spring Boot and Drop Wizard and Wildfly, even though it's not part of Java 8. You can use these libraries and achieve that. I'm sure very soon it will be part of standard Java, so every application will have endpoints. And the next principle is listening to events that are coming from the platform. That means the platform now owns the lifecycle of your application, so it can stop your application at any point, and your application has to listen to signals such as seekterm, seekkill, or maybe if you have to do some initialization logic, you can use post start to do some warming up of the cache, etc., etc. But the point being, now your application has to listen to these signals, and when Kubernetes sends a seekterm, your application has to shut down, otherwise it will get killed after 30 seconds. So it's important to listen to these events. The next principle is, I've called it process disposability, and the idea is your application should be ready for basically instant quick startup and instant shutdown. So because it can be shut down by the platform for any kind of reason, maybe your application is just being scaled down and Kubernetes is stopping your instances, so your application should be able to quickly shut down, and you should not rely on a certain instance of application. If you have some state, it has to be replicated, or it should be externalized rather than being in memory, because it can be killed at any point. And the last one, which is called runtime confinement. I see many places where they see Docker only as a box with all the dependencies of your application, but actually it's a multi-dimensional box, because at runtime it also has resource usage dimensions, so memory usage and CPU usage. And you have to kind of, with early testing, have to discover those, how much memory and how much CPU your process needs, and you have to tell that to the platform when you are running your application. So Kubernetes has to know these values in order to do effective placement and scheduling. Otherwise, at some point, your cluster will run out of resources and it will start killing your containers, because Kubernetes doesn't know how much resources your containers need. So it's really important to discover these values and pass those to the platform. Apart from these principles, which are kind of fundamental rules, there are lots of what's called best practices around containers in general. I picked here a few with links to container best practices, like images should be small as possible, and you should not rely on certain users like root or sudo to run, and you have to declare your ports and volumes. And it's a good idea to use labels to define what kind of APIs your container provides. All these are good practices that you should follow, but the previous principles will kind of make sure if you follow them, your container can be effectively managed in a cloud-native platform. So we basically, if you think about our journey, you have chosen an ecosystem. Hopefully that's Kubernetes, and you have to learn these primitives, the new abstractions and primitives the platform provides you, and follow some of the principles for creating good containers. And then I would say when you start solving the same problem again and again, you realize there are actually repeating patterns. And in the previous talk, Roland talked about the patterns. So here I'm going to just quickly touch on those. I'm not going to go into details, but because there are new primitives, there are now different ways of combining these containers together and name them as patterns. Three of the most popular patterns are the sidecar, ambassador, and adapter. As described previously, they've been first described by Brendan Burns, one of the other Kubernetes founders who now works on Microsoft, and he has written a white paper where these patterns are described. But the idea of sidecar, for those who haven't been here in the previous talk, is you can have two containers in the same pod which collaborate. So you have a main container, which maybe with your application, and another container that provides additional capabilities. And these two containers doesn't have to know about each other. They communicate over, they can communicate over a file system or some kind of IPC mechanism or through localhost, because the pod abstractions guarantees that the two containers belonging to a pod will be always deployed to the same host, so they can talk to each other easily. Basically, that's sidecar pattern, and there are more and more usages of this pattern. For example, things like circuit breaking, timeout, and all that has been moved into sidecar. Two specializations of the sidecar patterns are the ambassador pattern and the adapter pattern. They are similar to sidecar because the idea is you have collaborating containers in the same pod, but using different names, I would say, describes better the intent of the use cases. So with the ambassador, the idea of ambassador is you have a helper container that simplifies accessing to external system. So maybe you have an external memcache system, and your main application doesn't have to know how to connect to this memcache cluster. Instead, it can talk to ambassador container locally, and the ambassador container knows how to talk to memcache. The adapter is the opposite of ambassador. So rather than using a helper container for outgoing traffic, it simplifies access from external system to your main application. It can be used by things like monitoring tools or log aggregation, where a central system requires a unified API, and that helper container can provide a unified API to the external tool and maybe gather metrics and logs from your main container. Now, there are lots more patterns that are emerging and being named and described. We've seen previously how many configuration management patterns there are, how many service discovery patterns there are, but there are also, I would say, patterns for simple use cases. For example, very often a requirement is, how do I have a singleton application? And in Kubernetes, that would be simply the simplest way would be just to say Kubernetes, keep one replica of my application. And that will be singleton. It still will be highly available because Kubernetes will perform health checks. If something is wrong, it will restart, but it will make sure there is only one instance. So that's kind of a singleton service pattern. If you want to do some initialization, there are init containers. If you want to run a container on each host. There are daemon services. For stateful services, there is a stateful set. So there are lots of new primitives and new patterns that are emerging in this area. And maybe you are wondering, why we should do all that. Like we're talking about ecosystem primitives, quite a lot of new primitive principles, new patterns, but why we should bother with the whole cloud native and Kubernetes. And here I've tried to put together 9, I couldn't find the 10th one, but 9 benefits of using Kubernetes that I found really helpful for developers. So let's go through this quickly. Say the first one is a self-service environment. So previously, an environment used to be a VM. So you have a VM or a group of VMs. You have dev, test, int environments, and they are usually VM. Dev is maybe one VM, and test is slightly more powerful environment, and you have load testing environment, which kind of maps to production maybe, or half of it. But the point is, environments were represented by VMs. But with Kubernetes, environment is not anymore a VM. So an environment is just a collection of resources you request, and you can create it instantly. You can have now environments for single developers. You can have an environment per service. You can have an environment just to try a POC and then delete it, and that environment can span to multiple VMs. It doesn't matter where it belongs. So environment is just a pool of resources that is isolated from all the other environments, and this is what you need. That's I would say is a real game changer for quickly starting a new projects, new services, having the ability to create environments yourself. So once you have an environment, the next question is how you place your application on that environment. And previously we had all these strategies. Basically, do I place one microservice per VM? Do I place multiple microservices per VM? And then there are these pros and cons, or maybe something in the middle. I place multiple microservices on an application server on a VM. I would say with Kubernetes, all that again goes away, because all you have to do is trust the scheduler to put your application, to place it on the right host. So if you have told Kubernetes how much resources your container will need, how much CPU and memory, Kubernetes will find the best node where to place your application. You don't have to say, put it on this node or on that one. So that's a kind of delegated responsibility. You don't have to care for that. Here I have an example of a couple of processes. The yellow one requesting 2 cores and 4 GB of memory. The green one requesting 1 core and 2 GB of memory. And Kubernetes kind of can find the best way of combining these pods on the available resources. I would say another benefit. So we have the ability to create an environment. Kubernetes can place our application on it. Then the next question is, when you placed it, how do you start and how do you stop it? Before Kubernetes, we literally had to maybe copy a var and check the logs that it's starting up, and maybe it reaches a certain location in the logs, and you say, yeah, it has started, and then copy it to the second application server, and if it doesn't start, you restart and continue the process. But with Kubernetes, there is a concept of deployment. So Kubernetes can actually, in addition to placing, it can start your application in certain order, and it can wait for it to be healthy before directing traffic to it. And out of the box, there are 2 deployment strategies. The rolling one, where in this example, I have three instances of the service with version 1.0. Rolling strategy will make sure that it stops only one instance of the old version and then starts one instance of the new version. This way, you never have downtime. You always have some instances running, but the downside being now the consumer apps may get an older version and the new version while an upgrade is in process. Another strategy would be the fixed deployment, where Kubernetes will stop all the instances of the old version, and then it will start the new versions in a sequence. In this case, you will have some downtime, but the clients don't have to worry about hitting a service with two different versions. They will either go to version 1 or the newer one. There won't be any kind of mix in the meantime. In addition to this deployment strategies, they also call it like release strategies. So with Kubernetes, you have all the means to do things like blue-green deployments, where the blue-green kind of represents two different versions of the same service. You will start the new version and direct traffic to the new one. If something is wrong, you can direct to the old one, and you can do that all just in Kubernetes without needing additional external tools. Or you can do things like canary release, where you just deploy the new version of a service, and you allow consumers to only a portion of the consumers to go to this new version, and this way you check how the application behaves. So you have all these mechanisms in Kubernetes to use. Another benefit it provides is for application resiliency. In the microservices world, in Java, typically that is associated only with histories, I would say. So if you have histories, it will do circuit breaking and retries and timeouts, and your application is resilient. But actually, if you read the release it book carefully, you say that the author there talks about multiple levels of resiliency and bulkheading. So histories will only help you to do bulkheading at thread pool level. It will create different thread pools for you. But actually, you have to think about having bulkheading at process level. That means split your application into two processes. So if a process for some reason dies, the other one can continue. And the next level would be at the host level. So don't put both processes on the same host, because if the host dies, then you still your application is still dead. And the next level is actually split those into different hardware. That means use different availability zones, different regions, different tracks, etc., etc. And here are examples where things like containers and Kubernetes kind of can help you make your application more resilient on top of histories. To isolate resources, so can prevent from things like infinite loops, memory leaks. If there is memory leak, SelfCheck will catch that, and your application will be restarted. Or something like history won't be enough to do all that. For things like fault bombs, all these are different kind of failure scenarios that containers combined with something like Kubernetes will help you. Roland touched on service discovery and load balancing. So just briefly, if we were not using something like Kubernetes, typically you would do that as part of your application. So you would have, as part of your producer services, some agents, maybe that's a Zookeeper client or something else that registers the service to a registry, and then on the consumer side, you again have an agent that looks up the service and invokes it. With Kubernetes, all that behind the scene as part of the platform. So the consumer service just can call the service by name, and the platform will do the discovery and load balancing. So you delegate this responsibility to the platform. Your microservice can be even smaller. Another example is batch jobs. If you have to, for example, copy a file at midnight, every day. In Java, you had the options of the JDK timer or scheduled executor service, but typically you have a requirement to have that highly available, so you want it to be persisted. Then you have to use something like CORS or Spring Batch. With Kubernetes, you can ask Kubernetes to start the container at midnight, where your application copies the files, and the container then goes down. So you can delegate the responsibility of scheduling or running your application at periodic intervals to the platform. You don't have to do that in your application. So it's a different use case where, again, the platform can help you. And say the last benefit I have is immutable infrastructure, or what call is executable application manifest. So in the Java, we lock down or make immutable the business logic. Then in Docker, we make immutable the runtime, but actually with Kubernetes, we can actually lock down and make immutable the actual solution. So the way you define your containers, pods, and things like resource requirements, all that is expressed in YAML files, which means they are tested. They are run from dev environment to all environments. So the knowledge of how much resources your application needs and on which environment is deployed, etc., is not spread over things like a Confluence, and some of that knowledge is in developer heads, and some of that is in the operational people head. All that is actually in YAML file, which is executed and run in every environment. So it's really beneficial to have this executable solution topology. So the key takeaways, I would say, with things like Kubernetes or cloud native, automate all the routine tasks such as environment creation, placing applications, health checks, restarts, and all that. All these tasks you had to do as a developer. Now all these are done by the platform out of the box. Another thing is you move more and more non-functional and cross-functional requirements from the application to the platform. Again, you don't have to do service discovery, circuit breaking, recurring jobs in the JVM. You can let the platform handle that. Yeah, that's again another main benefit. And the last but not least, the ecosystem matters. So it is important on which cloud native ecosystem you will end up, and what primitives you get and what patterns emerge from that. This talk was an example of Kubernetes, almost done. So if you are not convinced from this talk, the good news is cloud native is not mandatory. So as the author put here, it's not survival is not mandatory, so you could continue doing the old way. But yeah, think about cloud native. I'm done with the slides. Sorry for all the noise and trouble. Have any questions?
No questions?
No questions then. Thank you for your time, and enjoy the rest of the conference.